Hello, welcome to my presentation. I'm going to show you how you can use Xilinx's new high-level synthesis for making a simple FIR filter. And I call this presentation abusing the tools because I'm not actually going to be using them in the correct way, using the entire suite for synthesis. I'm just going to be using it to generate Verilog and using the old ISE project. So this might be a little closer to something that you actually find yourself needing to do. And for the hardware that I have here, there's a vector network analyzer, which is a low-cost VNA device, and this is my analog portion. So there's an FPGA board from DLP Designs, and I've built a ADC and DAC to connect in. So to start with, I have a basic ISE project, and this basic project reads the ADC in and just puts it out to the DAC. So I can open that project here, and you can see we have this line. So what we can find is that I'll make sure the file is loaded here. And, oh, the wrong file is loaded. Let's just reprogram this. And we'll see sort of what the characteristic looks like. So it's sampling at 120 megahertz. So you'll kind of expect to see it go a little crazy when you hit the Nyquist frequency around 60 megahertz. And yep, you see, so this number 2 here, this is about 60 megahertz right there. So I'm only going to measure to say 50 megahertz, 1 to 50 megahertz. To get it a little flatter. And to give us a baseline to sort of get rid of these effects here, the final thing I'm going to do is I'm actually going to recalibrate straight through this device. So this will give us a 0 dB reference along the entire plane. We might have to undo this later. We'll see if it goes a little crazy. So now pull this down. So there we go. So I've sort of facetiously made it go to 0 dB. We're going to see some odd effects here probably later on, but it is a little nicer. So the next step is you start the Vivado HLS, and we're going to go ahead and create a new project. And I'm going to put these somewhere else. And you just basically save it anywhere. And we're going to make a new file, and I'll call it, save it. Where do I want to save it? So right here, I'll just call it fir.c. And where was this saved? And give it the top function name, FIR. I won't bother with the test bench right now, and again, we'll just select a random part to give us output Verilog. You have to be a little careful doing this random part selection that I talked about last time, because it may try to use resources that don't exist in the file you want to use. So, there we go. And as before, we include this APCint to give us the arbitrary integers. And this will be the main function, FIR. And what it'll have in it is there'll be the input, and they come from the ADC. It's a offset decimal format, and this will be the X. Oops, I did that backwards, didn't I? You went 10 pointer. Just pull up. And yeah, they are 10. Sorry, I was just checking the datasheet. You went 10 pointer X, volatile. You went 10, and this is the output to the DAC. So you could, if you want, just assign these as a test, but that's a little simple. So I'll save that, and the next thing I'm going to do is insert some directives here, and I save them in the source file. And as I said, I'm going to use FIFO's here, and FIFO for this one. We'll see later we could have got away with a different format, but I like the FIFO. They're simple, simple to start with. So the next thing we're going to do is we're going to start with doing some data formatting. When we input this offset decimal, we want to convert to a int. So I'm going to create a int 10 instead of a uint 10. This will be the int value. And I'm just going to make this function go forever. And it's going to read in the input. Int value equals, and because we're using the FIFO, we do it this way. And write the int value. So this isn't too interesting because we also want to check that the conversion was done correctly. So when I say the conversion, I mean converting from the straight binary to the 2's complement, so the sign notation. And how we do this is I'm going to tell the compiler to first sign extend the input value to an int 11 type. And then I'm just going to subtract the offset off, so halfway is 512, and I'm going to tell the offset to be int 10 at least. And this should give us an OK value. When we write the output, we again need to convert back up. So I'm going to take this int value and I'm going to add, I guess 10 should be enough, add 512. And I'm going to force it to be a uint 10. Alright, so there's a very simple beginning program. So we can use this and we'll insert it and test at least this much work. So hit run C synthesis. It checks it over. Alright, we're done. So it's created the Verilog file. So we go back to the project navigator and we'll add that source. Oops. And you can't see, this window's too big. But all we do is we add a reference to where that FIR.v is. And there you can see it being added. Alright, so here's the file. And we'll just use this module interface here. So we're going to replace this. Instead of directly assigning it, we're going to go through the Verilog module. So we'll just convert these into ports. Connect up the clock. I don't have a reset in this very simple example, and I'm just going to tell it to always start. Because it goes into an infinite loop, I can do that. The input data is ADC data. We have this FIFO input, so we're going to actually tie the empty high, so it's just ignored, reads ignored, and the data out goes to the DAC, and the DAC, because I'm cheating and using this FIFO interface, the DAC is always never full. Alright, there we go. So you can run generate programming file. That'll take a second. So in the meantime, we can look back at our, oops, where's that other one? Look back at our file here and decide what we want to do next. So now we have to actually look into the design of the FIR filter So as you might know, it looks something like this. We'll have these b constants times a finite number of x values. And that means, for example, if we had a length of 3, we would be taking b0 times x2 plus b1 times x1 plus b3 times x0. On the next iteration, effectively, these would all shift over. So x0 new would become x1, would take from x1, x1 would take from x2, and x2 would be the new value in. So we need these coefficients, and you can use something like MATLAB, or actually I'm going to use this online tool to do it. And in the meantime, oh, there we go, this is done. So I'm going to reprogram the FPGA. And yep, that's the right one. And we can see that works fine because it's connecting the input to the output. So that is basically exactly what we expect. So my basic device has worked. So next, as I said, we're going to look at the FIR filter. So we need to bring back this. And now we're going to try to start to put some of the structure of the FIR filter in place. So we have a while loop. The next thing I'm going to do is I'm actually just going to read in that input data. So how I do this is I'm going to create these x values, xstore I'll call it, whatever the length of the filter is. I'm going to use 19 taps. So this xstore is going to be this right here. So these x values is going to be xstore. So we need to, on every iteration, we're going to have to do this update process, which is simple enough. And I'm just going to create a generic integer to use for a loop here. And the loop will just look something like this. So for I equals 0, I is smaller than FIR length. So go through all the taps. And xstore I is equal to xstore I plus 1. So actually what you'll notice is that we don't want to overwrite the very last one because this will be the new data. So we go to one less tap. And the new byte is actually, so this is the final byte, and this is where I do the same input here. And what I should see is that ideally if I assign int value to xstore 0, the result of this should just be that it's delaying going through everything. So I can run synthesis again, and we'll take a look at what it does. Ideally, if I program this again, I expect to see everything to work. But before we do that, I run synthesis, and we can take a look at this loop. So it's created this loop 1, and there's this big latency here. This is sort of, we didn't constrain anything, and it's actually running these loops as they're written, so to speak. We want to pipeline them because we want, on every clock cycle, we need a new data out, because one data in, one data out. So this while statement, I'll put a directive in the source file, and I'm going to say pipeline. And this II means how often do I get new data out, and every single cycle I get new data out. So we run synthesis again, and we take a look at the report file. You should always be checking these. So summary, loop 1, it's saying this is the only loop. Pipeline, this II is 1. So it managed to achieve what we absolutely need in this. So once again, we can run synthesis. Hope for the best. And while that's going, let's continue to look at the rest of the FIR filter. So we have data shifting through. The next thing we need to do is actually apply the filter. So this is one aspect there, and the next aspect is going to be the actual multiplication of all the filter coefficients. So the same thing, I'm going to loop through. It's worth noting when I apply this pipeline directive, it's automatically unrolling these loops. So there's lots you'll have to read when you actually start doing this. But I don't have to explicitly tell it to unroll all these loops to achieve that pipeline. It'll figure that out. So there we go. That's the beginning of the loop. And we're going to need to do fixed point multiplication. If you're using C++, it has an ability to help you automatically do this. There's a class. For C, there's no such luck. So I'm going to choose first the filter coefficients, bcoef, and they're also going to be 10-bit numbers, so you should really validate what the effect of doing this is. And we're just going to preload them. For now, I won't worry about it. So we have a 10 by 10. Obviously, this intermediate value of the multiplication is going to have to be 20 bits. So what I'm going to do is just directly from the formula here, bk of x and minus k, I'm going to write this equation. So I'm going to write x int sum equals bcoef I times x, and remember x stores our x values, and FIR length, we have to account for the off by 1, FIR length minus 1, minus, I. So there we go, it's that simple. And the final thing we also have to do is we then want to get our fixed point back. So we've multiplied it 10 by 10. Remember, 1 bit is used for the sign. So actually what I'll do now is shift left 9, and this will get me back to the point. If you want to check sort of if you've done this correctly, just do on paper a simple example. So let me give you an example here. Just start a new slide. So let's see, 0.2 times 0.9. And if you do this out, 0.18. So 0.2 times 512. Remember, I'm using 512. It's 10-bit, which is 1024, but it's ranging from +1 to -1. So I need to half that. So 0.2 times 512 equals 102.4, and we round. 0.9 times 512, let's just make it negative for fun. Oops. Just so you remember, this is why we do it. 460.8, 460. So 102 times 460 equals 46920. So this is the result of the signed multiplication, and what I'm saying is that I need to shift left 9 bits, which is equivalent to 2 to the power 9, which is 512, which is equal to 91. So now 91.6, and this will just become 91. So is that the right answer? I go, well, 91 divided by 512, because now I'm converting back to floating point. Or Yeah, so there we go. So you can see here I've converted, here I've done the multiplication with decimals, and here I've converted back, and it's the same. So that's the right conversion. Returning back to this project, remember I had just inserted the delay line in here. So I was just checking that the X values were working properly. Ideally, you can do this all through test benches, and you can get some nice simulators that'll interface with MATLAB for helping you do some of the test benching. I'm trying to show you just the HLS stuff now, so I'm sort of skipping out on that. And again, it's worked. We see that there's a little oddity somewhere, but basically it's worked well enough. Okay, here we go. There's the FIR filter. And the final part of the filter is the summation. So we need this int sum. And what should the size be? Well, that intermediate value is 10 bits. And if this FIR length, say I want up to, 32, 2 to the power of 5 is 32, so I'm going to use a 15-bit integer to make sure I don't potentially overflow. You might be able to get away with smaller depending on your coefficients. I'm just going to keep it safe here. And I call this, I'll call int sum. So int sum plus equals x int sum. And remember, I want to clear it before we begin. All right, there we go. So actually, now all I do is that, and this should work now. So that should be a complete FIR filter. The last thing I need is the coefficients, as I said. So how I'm going to do this is I'm going to use this website to generate them. And I'm running at 120 megahertz. I can't use that high frequencies here, so I'm just cheating. 19 points, and let's say I want a 15 to 25 band stop. What's that look like? And we'll let it get a bit messier. Yeah, something like that. So these are all in decimal sort of notation. We need to get these into fixed point, so all we're going to do is, you can use anything. I'm going to use MATLAB here, and you can use something like Python if you don't have MATLAB. It works just as well. So I'm going to say dump that numbers in there, so there's the fixed point, and I'm just going to convert them again. I'm going to sine 10-bit, convert them to 512, and then round them. And these will be my filter coefficients now. So I just copy them, and we put them right in the HLS. So I'm just using them as fixed coefficients when I initialize this variable. There we go. And hopefully this will work. So we run synthesis again. We give it a second, and we always check the results here to make sure it's kept the proper, so it's pipelined properly, and check that there's no extra files we needed to add. Nope, just the one. Go back to this and hit generate. So this will take a second. What else do I have here? So this is just explaining how I did that coefficient conversion. So I took them and multiplied by example. I'm using 10 bits to represent the FIR filter coefficients. 1 bits for the sine, so 2 to the power 9 is 512. So I just multiplied each coefficient by 512. And there's just how I put the module in place. So this high-level synthesis, you can see it's a pretty quick way for doing designs. Either, in this case, I'm sort of showing you a hack engineering prototype, but it has a lot more features for doing complete reliable designs, including the test benching. Some of this streaming input and output is a lot easier if you use the C++ version, but I think more people might be familiar with C, so there is some advantage to using that. So let's just program that. And see how we did. There we go, not too bad. So that's at about 20 megahertz, and let's compare. So that's what it was claiming we're going to get. So, pretty cool. You can see it works really well, and a really easy way to design FIR or sort of any sort of processing block using C, and then converting it straight to Verilog. So thanks for watching, and hope you found this useful. All the files are going to be on a link if you look in the video description too.